Hey, Wheaton North, Mr. Yergler here. We're going to talk about quantum numbers. So this will be a short video on just quantum numbers, kind of getting a little extra practice with assigning the right quantum numbers to any given electron. All right, let's get started. All right, the four quantum numbers are they're denoted as n, l, m sub l, and m sub s. Okay, and these tell us specifically where electrons are in the atom. So it's kind of like an address. Like n would be analogous to like what city you live in. L could be analogous to what street you live on. M sub L could be what your house number is, and then M sub S could even be like what room you're in, for example. So we're getting more specific as we go through these quantum numbers. Okay, the first one, n, is the principal quantum number. This is just the energy level, so it's either 1, 2, 3, or some other integer. As far up as 7, theoretically it could be higher than that, but all the elements on the periodic table are somewhere within the first 7 energy levels. L is the angular momentum quantum number. This is essentially the sublevel. Electrons are arranged in one of the sublevels within the energy level. So that might refer to the S sublevel, or the P sublevel, or the D sublevel. And L can be anywhere from 0 to n minus 1. We'll look at an example in a second that'll make more sense. M sub L is the magnetic quantum number, and this can be anywhere from negative L to positive L. So for example, if L happens to be 3, then M sub L can be negative 3, negative 2, negative 1, 0, 1, 2, or 3. This refers to the specific orbital. So we represent that specific orbital by one line on an orbital diagram. Or you could represent it by saying the px orbital, or the py orbital, or the pz orbital. The last one is the spin. The spin quantum number, and this is either plus or minus a half. We show this on orbital filling diagrams as an up arrow or a down arrow. The Pauli exclusion principle says that no two electrons in an atom can have the exact same four quantum numbers. So if we have two electrons that are both in the same energy level, which is possible, they could both be in the same sublevel, and they could even be in the same specific orbital, but they can't have the same spin, and that's why we represent them as an up arrow and a down arrow. If those first three quantum numbers are the same, then the last one has to be the opposite. Let's look at an example. This is a picture of phosphorus, and we're going to look at one particular electron. First, its principal quantum number. In this case, as this is shown, this is a Bohr model, which is overly simplified, but it kind of helps to kind of picture what's going on and where we're at in the atom. We're on the third shell, or the third energy level, so our principal quantum number in this case is 3 for this particular electron. The angular momentum quantum number, again, refers to the sublevel. If n in this case is 3, then L can be either 0, 1, or 2. L cannot be 3 because in this case we're talking about the third energy level. An angular momentum quantum number of 3 can only exist if we're talking about the fourth energy level, in which case n minus 1 would then be 3, and we can go up that high. But if we're talking about energy level number 3, then the most L can be is 2. Okay, so we have 3 sublevels. And these 3 sublevels correspond to our S, P, D, and F sublevels. So L equals 0 is S, L equals 1 is P, L equals 2 is D, and so on. The next quantum number would be the magnetic quantum number. Now we're talking about specific orbitals. Again, a specific orbital refers to like the line that we draw, not the S, P, D, or F. Sometimes we may accidentally refer to these as orbitals. These are actually the sublevels. Within them are the orbitals. So let's look at each of these individually. If L equals 0, then M sub L can only be 0 because positive and negative L is still 0. If L equals 1, then M sub L could be negative 1, it could be 0, or it could be positive 1, anywhere from negative L to positive L. If L equals 2, then M sub L could be negative 2, negative 1, 0, 1, or 2. Notice the numbers of specific orbitals. The D sublevel has 5 of them, the P sublevel has 3 of them, and the S sublevel only has 1. And this corresponds to the number of elements in the periodic table in that section of the periodic table. We have 5 orbitals in the D block, which each hold 2 electrons, and so we have 10 elements in that block. If we continue the pattern, if L is 3, then in the F sublevel, m sub L can be anywhere from -3 to +3. The last quantum number again is the spin, and that is represented by just an up arrow or a down arrow. We could also say that each of these lines represents the px, the py, the pz. So when we're talking about specific orbitals, we sometimes represent those with lines. Sometimes we could represent them by saying px, py, pz. There's also a way to represent them in the d and f sublevels, but they get really complex. You can have d x squared minus y squared, for example. All right, so that's just a quick example of quantum numbers and assigning quantum numbers and kind of understanding how these are related to both the periodic table and to each other. All right, this is Mr. Ugler signing out.